In this video, we are going to quickly look at a method of factoring higher order polynomials that are quadratic in form. Now, we've probably spoken about this before, but just to remind ourselves what quadratic form is, if it's like a quadratic function. So a quadratic function would be ax squared plus bx plus c. But we don't necessarily have to have x as the thing that's squared. So anything of the form a question mark squared plus b question mark plus c is quadratic in form. This could be e to the x, it could be sine x, so we can have quadratic form in lots of different cases. When we're working with polynomials, we might have something like a x squared plus b x squared plus c. And so when we simplify this, we would have a x to the fourth plus b x squared plus c. But we don't have to stop there. Suppose instead of having x squared as the thing that were quadratic in form, let's say we started with a x cubed squared plus b x cubed plus c. In this case, remembering that a power to a power, we multiply the exponents, gives us a times x to the sixth plus b times x cubed plus c. All of these expressions are in quadratic form, so we can factor it just like a quadratic function. In particular, we're going to factor it using the x box method. So the example I've written up here is x to the fourth plus 12x squared minus 64. Now, because you've already factored quadratic equations before, I want you to pause the video and see how far you can get factoring this. And when you've gotten as far as you can go, play the video again, and then we'll solve it or factor it together. So by now, you've paused, you've done your work, maybe you got stuck somewhere, or maybe you finished and want to check your work. So now we're going to go through solving it together. I'm going to set up my x. On the top is a times c, which is negative 64, and on the bottom is 12. So I need to identify two numbers that add up to 12, multiply the negative 64. If you've done the work already, you may have found that these two numbers are 16 and negative 4. So we can factor this expression as x squared plus 16 times x squared minus 4. Now we shouldn't just stop there. We should always see how far can we go. Can we continue to factor each of these terms? So if we look at this first one, if I write 16 on top, 0 on the bottom, there's not any real numbers that work. But what I can do is find the solutions, and then by the factor theorem, which we reviewed previously, we can use those zeros to make our factors. So if we start with x squared plus 16 equals 0, we subtract 16 from both sides. We take the square root of both sides. The square root of 16 is 4. And then the square root of any negative number gives us an I, that imaginary unit. And since we are solving an equation by our fundamental theorem of algebra, x squared plus 16 has two solutions. So we need to make sure we have the positive and negative square roots. As our factors, that would be x plus 4i times x minus 4i. Now we're done with that first part. Let's come up to the second factor. This one's going to be a little bit nicer because we can use the x box. Negative 4 is 0. And the numbers, if you haven't already figured this out, are 2 and negative 2. So we have x plus 2 and x minus 2. So we can completely factor using the repeated process of factoring a quadratic. We can completely factor x to the fourth plus 12x squared minus 64 to the linear factorization x plus 4i times x minus 4i times x plus 2 times x minus 2. Now, if we wanted to go one step further and identify these zeros, we would have negative 4i, positive 4i, negative 2, and positive 2. And since the exponent for all of them is 1, the multiplicity of each 0 is also 1, which makes sense. If we have 4 distinct 0 and a 4th-degree polynomial, then the highest multiplicity that they could each have is 4, because the sum of our multiplicities has to add up to the degree of our function. So in this very simple exercise, whether we say it explicitly or not, we're relying significantly on things like the factor and remainder theorems and the fundamental theorem of algebra and the conjugate pair theorem. But because these things become second nature with practice, we often don't bother mentioning them in the process, even though, as we can see, they're always present, helping us to figure things out. So this has been an example of factoring something in quadratic